Okay, I'm going to finish off chapter 2 by doing some large dataset exam questions. There are some exam questions that are in the Bison Maths Google Drive that are not about the large dataset, but I wanted to pick 3 because my students always say to me that they want more practice on the large dataset. So let's read through this question. Joshua is investigating the daily total rainfall in Herne from May to October 2015. Using the information from the large dataset, Joshua wishes to calculate the mean of the daily total rainfall in Herne from May to October 2015. Using your knowledge of the large dataset, explain why Joshua needs to clean the data before calculating the mean. Well, one of the things that you should know about the rainfall data is that many of the days say TR. So one of the things is that the trace values need to be converted to numerical data first. Because at the moment, you can't input anything if it says TR, okay? Using the information from the large dataset, he produces the grouped frequency table below that I've got over here. And it first of all wants us to use linear interpolation to calculate an estimate for the upper quartile of the daily total rainfall. So we're going to do the calculations now for part B. We're going to find out which one is going to be the upper quartile. So I guess the first thing I'm going to need to do is to find out how many things there are in this table. So I'm going to add up all of the frequencies. So that's 121, 10, 24, 12, and 17. So that is 184. Just double checking I've got those all typed in right. So there's in total 184 here. So for the upper quartile, we're going to do 3/4 of 184. So I'm just going to multiply that by 0.75. So it's going to be the 138th term. So I'm going to go back to this table and I'm going to fill in the cumulative frequency. So I'm going to have 121, 131, 155, 177, and then 184. Now we're looking for the 138th term. So the 138th term is going to be inside this group here between the 131 and the 155. So let's draw out what our table would look like. It's going to go being between 131st to the 155th. And we're looking for the 138th term, which is probably going to be a bit down this end. So there's my upper quartile. I guess I could have called it here Q3. I don't really mind, whatever you want to call it. And that's going from 1.0 to 5.0. So my calculation for Q3 is going to be 1 plus this fraction, so that's 7 out of this whole group here, 7 out of 24, multiplied by the fraction on the bottom, or the length on the bottom, excuse me, which is 4. So it's 1 plus 7/24 of 4. So it's 2.17. 2.17 millimeters, and I'm just going to say that that is to 2 decimal places. Okay, so part C, it says calculate an estimate for the standard deviation of the total daily rainfall in Herne from May to October 2015. And you'll notice they've given us some summary statistics down here at the bottom. So we know how to find the standard deviation. The standard deviation is going to be the square root of the mean of the squares. So this is doing your 7704.1875 divided by how many there are, minus the square of the mean. And the mean is going to be 539.75 divided by 184 all squared. So that's the mean of the square values minus the square of the mean. And it's just going to be as simple as getting this rather annoying thing typed. So it's 7704.1875 over 184 minus, open the brackets and do a fraction, 593.75 over 184, close the brackets and square it. And so the standard deviation is going to be 5.61 millimeters, and that's to 2 decimal places as well. Okay. So we've done A, B, and C. It then says for part D, state the assumption involved with using class midpoints to calculate an estimate of a mean from a grouped frequency table. Well, we mentioned this way earlier on at the beginning. By using the midpoint, what we're actually assuming is that the data is uniformly distributed or equally distributed in these groups. So for D part 1, what we have assumed here is that the data is evenly or uniformly distributed in the class intervals. That's what we have assumed by using midpoints. It then says for part 2, using your knowledge of the large data set, explain why this assumption does not hold in this case. Well, if you have a look here, the most common one is this. There's 121 days where the rainfall was between 0 and 0.5. And it doesn't take much to realize that between May and October in 2015, there are going to be lots of days where there was no rainfall at all. And so it's not uniformly distributed. Now, yeah, you do need to know the large data set, but a bit of common sense will tell you that there are going to be not an even distribution in this part. There are going to be many 0 pieces of data. So it says, explain why this assumption does not hold in this case. We should say there are many zeros in the large data set. So the first class interval won't be uniformly distributed or won't have data. That is uniformly distributed. Okay, part 3, it says state giving a reason whether you would expect the actual mean daily total rainfall in Herne to be larger than, smaller than, or the same as the estimate based on the grouped frequency table. So if we think that there are going to be loads more zeros, that should reduce the mean. Because if we think there are more zeros than is being accounted for, we think this will reduce the mean. So the additional zeros will mean that the actual mean will be smaller than the estimate. Okay, let's have a look at the mark scheme. So let's remind ourselves of our answers. We've got 2.17, 5.61, okay. So we've got the trace data needs to be converted to numbers. We said that. 2.17 for the upper quartile. 5.77. Oh, I must have typed something in wrong there because this all looks correct. I must have just done something incorrect on my calculator. Let's see if we can spot the error. I did 593 and it should have been 539. So let's just correct that. See how easy it is to make these mistakes. This should have been 539. So I'm going to go back to here. 539. So it should have been 5.77 millimeters. So I wouldn't have got those marks there. I would have lost this mark, but I would have got this mark, which is interesting to see. Then says for the last parts, using the class midpoints, assumes that the values are uniformly distributed. We said that. Assumption doesn't hold. The majority of the data in the first class is 0. The actual mean is likely to be smaller. The first group has more values at 0 here. Okay, let's go on to the next question. Hopefully I won't make any calculation errors. So it says the daily mean air temperature from the large data set for the month of June 2015 in Jacksonville is summarized in the table below. So this is for Jacksonville in June 2015. Use your calculator to estimate the mean and the standard deviation of the daily mean air temperature from the large data set for Jacksonville. Give each of your answers to 3 significant figures. So I've actually already put the data, I think, on one of my calculators. Let me see if I've got it on this one here. Yep, so I'm going to just show you what I've got here. I'll put the camera on, and I've used the midpoints, okay? So for the midpoints that I've got, you'll notice I've used 23, 24.5, 25.5, 26.5, 27.5, and 30. And you'll see that I've filled in all of the frequencies, okay? If you're not sure how to find the midpoint, just make sure you add the upper and lower boundaries and then divide by 2. So I'm going to go to one variable calculations, and I've got all of the information that I need there. Okay, so I'm going to just fill that in onto my page. So because it's only a 2-mark question, I don't think I actually need to do any of the method for this. So all it wants me to do is to say what the mean value is. So I'm going to use the same letters they've been using. I would say that the mean value for Jacksonville from my calculator is 26.6. And that's in degrees centigrade. And then the standard deviation, they want it to 3 significant figures, is 2.09 degrees centigrade. Okay. If it was 3 marks, I probably would do the method for this one. But for 2 marks, it is just going to be 1 mark for this and 1 mark for this. It then has a completely different thing. It starts talking about a different place. It says that the mean and standard deviation for the daily mean air temperature, so we're still talking about the daily mean air temperature for Perth in June 2015, are 14.8 and 2.37. So this one is the mean, and this one is the standard deviation. The minimum daily air temperature in Perth is 8.8, and the maximum daily air temperature is 18.5. Using limits for outliers of the mean minus 3 times the standard deviation and the mean plus 3 times the standard deviation show that there are no outliers in the data for Perth. Now, this is technically coming up into the 3rd chapter, but I think it's pretty easy to do. So what we're going to do is we're going to do the mean minus 3 times the standard deviation. So I'm going to do the mean minus 3 times the standard deviation to get the lower bound. So that's the mean minus 3 times the standard deviation, which is 7.69. And then the upper bound is the mean plus 3 times the standard deviation. So you can just go back here, change it to a plus. That's 21.91. And because the minimum was 8.8 and the maximum was 8.5, there are no outliers. So we just need to explain that. So data less than 7.69 and bigger than or greater than 21.91 are outliers, but the min and max for Perth are both inside this range, so there are no outliers. Okay, it then says, assuming each location is typical of the hemisphere it is in, so you're either in the northern hemisphere or the southern hemisphere, which half of the Earth, suggest what these means and standard deviations imply about the relative daily mean air temperature in June 2015 in each hemisphere. Give reasons for your answers. So they're asking us to comment about the air temperature in each hemisphere. So we should say Jacksonville, which is the northern hemisphere, we have the mean we calculated was 26.6 and the standard deviation was 2.09. For Perth, which we know is in the southern hemisphere because it's in Australia, they've told us that the mean was 14.8 and the standard deviation was 2.37. So they want us to compare 2 things. They want us to compare the means and the standard deviations to say what that means about the hemispheres. So let's have a look at the means to begin with. The mean in Jacksonville is much higher. 26.6 is much higher than 14.8, is much higher than in Perth. And what does this say? It says, suggest what this means about the temperature in each hemisphere. So the mean in Jacksonville is much higher than in Perth, implying that the northern hemisphere is hotter than the southern hemisphere. In June 2015. However, the standard deviations are similar, implying they have a similar spread. Of temperatures in the hemispheres. Okay, it's quite a lot to have to do that for those 2 marks, but it's not bad. And then it just says comment on the validity of the assumption in 1. So we have just tried to make a comment about the northern hemisphere and the southern hemisphere. And you should be thinking to yourself, I wonder if that is a sensible thing to do. Well, it's probably not going to be valid because we've only been looking at 2 locations. This is probably not valid. As we have only looked at 1 location from each hemisphere. So likely not representative. It kind of seems crazy to just say like, oh, well, because Jacksonville's in the northern hemisphere and Perth's in the southern hemisphere, this is what must be true about the northern and southern hemispheres. It's just not enough information. So however you want to explain that. So we got the right answers of 26.6 and the 2.09. And there's just a different method of how you find standard deviation, but we always do this one up here. We've got the marks about there being no outliers. The mean for Perth is lower than the mean for Jacksonville, which suggests that it's higher in the northern hemisphere. That's what we said. The standard deviations are similar, which suggests similar levels of variation in each hemisphere. Again, we said that. This is based on 1 location in each hemisphere and therefore is not valid as temperatures are likely to vary across each hemisphere. So I feel like we got those nice and clear. Okay, last question that we've got. Again, it's on the large data set. So this one says the number of hours of sunshine. So we've got the hours of sunshine each day. Why? For the month of July at Heathrow are summarized in this table. I'm going to skip part A because this is a chapter 3 topic. Use your calculator to estimate the mean and the standard deviation of the number of hours of sunshine each day for the month of July at Heathrow. Give your answers to 3 significant figures. Now, because it's 3 marks here, for the standard deviation, there is going to be a method mark. So I'm going to actually write out what I would do for the method mark for that. Now, I've got all of the information on my calculator. I've put in the midpoints. My midpoints I've used are 2.5, 6.5, 9.5, 11.5, and 13. I'm not going to show you all of this on the calculator. I think it's a bit boring for you to see. But I can just use my calculator to do some of these calculations. So the mean value, they've used the letter y. So y bar is 6.63 hours, and that is to 3 significant figures. And this time I'm going to show my calculations. So I'm going to do the mean of the squared. So I'm going to do getting this from my calculator, 1785.25 over n, which is 31, minus 6.63 squared. Now, after I've written that for the method mark, I'm still going to write down what my calculator has told me, which is 3.69 hours to 3 significant figures. So I just do that to get a method mark, but that's really where it's going to be at for getting the correct answer. So I don't know why I called that part A. We skipped part A. Here is part B. Let's make sure we read this really carefully because we don't want to just go to the numbers. We want to make sure we know what it's talking about. It says that the mean and standard deviation for the number of hours of daily sunshine for the same month in Herne are 5.98 hours and 4.12 hours respectively. So we need to make sure that we've clocked that this one is talking about Herne this time, and it's given us some different values of the mean and the standard deviation. Thomas believes that the further south you are, the more consistent should be the number of hours of daily sunshine. State, giving a reason, whether or not the calculations in part B support Thomas's belief. So what we've got is if we're talking about consistency, because that's what he said, that the further south you are, the more consistent should be the number of hours of daily sunshine. Consistency is to do with the standard deviation. If it is more consistent, you have a lower standard deviation because it is less spread out. So let's compare them. We have the standard deviation in Heathrow is 3.69, but the standard deviation in Herne is 4.12. So the standard deviation shows that Heathrow has a more consistent number of hours. But Heathrow is north of Herne. Herne is on the coast. Herne is on the south coast. So I've said here, do they support Thomas's belief? He says that the further south you go, the more consistent. But we've said that Heathrow has more consistent number of hours and it's north of Herne. So what does this say about Thomas's belief? This does not support Thomas's belief. Quick side note, the locations, they go Camborne, Herne, Heathrow, Leuchars, and Leeming. So I remember them as going like in alphabetical order: Camborne, Leuchars, and Leeming. Leeming Leuchars, excuse me, Leeming, Leuchars, and then these two are the other way around in alphabetical order. The Heathrow is up in London, and then Herne is more south down here. You can check out my video on the large data set if you want to hear about how I remember some of these things. Nearly there. Estimate the number of days in July at Heathrow where the number of hours of sunshine is more than one standard deviation above the mean. So we're going to be doing, for part D of the question, we want to find out more than one standard deviation above the mean. So I'm going to figure out what that value is. This is the mean, and I'm going to add on one standard deviation to that. So I'm going to do 6.63 plus 3.69 is 10.32. So I'm going to figure out how many days are there more than 10.32 hours. So it's going to be somewhere inside this group, okay? The ones that are more than 10.3 hours, well, did it want more? And the number of hours is more than one standard deviation. It's going to be 1, 2, 3, 4, 5. We need to find out how many of that group I've underlined in blue would be more than 10.32. So that group goes from 8 to 11. And we've got 10.32 up here. And the whole group, there are 8 days in there. So I need to find out what is 11 minus 10.32. What is 0.68 out of 3? I'm calculating the fraction up here, 0.68 out of 3 of 8. It is 1.81 days. So days with more than 10.3, 2 hours, are going to be the 1.81 from that group, plus the pink numbers, which are 3 and 2. So 6.81 days, which we would round to 7 days to the nearest whole number, because you couldn't give a half day for this. Okay, let's check our answers here. So we got the 6.63, the 3.69. The mean of Heathrow is higher than Herne, and the standard deviation is smaller, suggesting that Heathrow is more reliable. We don't need to worry about the bit about the mean. It's just about talking about the standard deviations. Don't know why they're talking about the mean. And then we've got 6.86, so 7 days. They did it with 10.3, I did it with 10.32, but we do get that bit of 7 days. Okay, so pretty tricky, these exam questions on the large data set, but there's not an awful lot of extra stuff you need to know. The main thing is about where locations are, northern hemisphere, southern hemisphere, and knowing some things about like the trace data that needs to be cleaned and things like that. Okay, bit of a long chapter, chapter 2, but nearly there.